Let E be a field, and let H be a finite group of automorphisms of E. Each automorphism is a way of rearranging E that perfectly respects both addition and multiplication. Now collect every element of E that is left completely unmoved by every automorphism in H. These fixed elements form a subfield, called the fixed field, written E to the H. Artin's theorem makes a remarkable promise. The degree of E over this fixed field is exactly the number of automorphisms in H. The size of the group equals the degree of the extension. To prove it, we will first need a beautiful lemma, due to Dedekind. Let us name everything carefully. Write H as a collection of n automorphisms, sigma 1, which is the identity, up through sigma n. Let F be the fixed field, the set of elements X for which sigma of X equals X, for every sigma in H. This set F is genuinely a field, closed under all the operations. And the degree, E over F, is simply the dimension of E as a vector space over F. Our entire goal is to show that this dimension equals n, the order of H. We will attack it from two sides, proving the degree is at most n, and then that it is at least n. First, Dedekind's lemma, on the independence of characters. A character is a homomorphism from a group G into the non-zero elements of a field E. It carries products to products. Field automorphisms are characters, acting on the multiplicative group of E. The lemma states that distinct characters are linearly independent over E. In plain terms, if some coefficients, a 1 through an, combine the characters into the zero function, so that the sum of ai times sigma I of G vanishes for every single G, then every coefficient ai must already be zero. No non-trivial cancellation can occur. Suppose, for contradiction, that a non-trivial relation does exist. Among all such relations, choose the shortest one, the one with the fewest non-zero coefficients, say m of them. Now m cannot equal 1, because a single non-zero term, a 1 times sigma 1, can never vanish, since a character is never 0. So m is at least 2, and sigma 1 differs from sigma m. Pick an element H where they disagree, so that sigma 1 of H is not equal to sigma m of H. Now we use the relation twice. First as it stands, for every G. Then we feed in H times G, using that sigma I of Hg splits into sigma I of H, times sigma I of G. Next, scale the original relation by sigma m of H, and subtract the two. The final term cancels perfectly, leaving a shorter relation. Yet its very first coefficient, a 1 times the difference of the two characters at H, is not 0. A shorter non-trivial relation contradicts our minimal choice. So no such relation ever existed, and the characters are independent. Now for the main theorem. Let n be the order of H, and F the fixed field. We will prove the degree, E over F, equals n by squeezing it between two bounds. First, that the degree is at most n. Then, that it is at least n, together, these force equality. And Dedekind's lemma will power the second half of the argument. For the upper bound, we show that any n plus 1 elements of E must be linearly dependent over F. Take elements alpha 1 through alpha n plus 1. Build a system of linear equations, one for each automorphism sigma j in the group. The jth equation reads, the sum over I of sigma j of alpha I, times an unknown xi, equals 0. That is n equations, but n plus 1 unknowns. More unknowns than equations always guarantees a non-trivial solution, with the xi living in E, and not all 0. Now take the shortest non-trivial solution, the one with the fewest non-zero entries, and scale it so the last non-zero entry equals 1. We claim that every xi actually lies in the fixed field F, suppose not. Then some automorphism tau moves one of them, so tau of x1 is not equal to x1. Apply tau to every equation. Because H is a group, tau composed with the sigma j simply reshuffles the very same automorphisms, so the system is unchanged, and tau applied to the solution is again a solution. Now subtract the two solutions. The scaled entry becomes 1 minus tau of 1, which is 0, producing a strictly shorter solution that is still non-zero. This contradicts minimality. So every xi lies in F. Finally, the equation belonging to the identity automorphism reads simply, the sum of alpha I times xi equals 0, a true linear dependence over F. Therefore the degree is at most n. For the lower bound, suppose, instead, that the degree were smaller than n, equal to some number m less than n, choose a basis, omega 1 through omega m, of E over the fixed field F. Now build a different system, this time with m equations in n unknowns, y1 through yn. The ith equation reads, the sum over j of sigma j of omega I, times yj, equals 0. Once again there are more unknowns than equations, since n is bigger than m. So a non-trivial solution exists, with the yj in E, and not all 0. Now watch what this solution does. Take any element x of E whatsoever, and write it in the basis, as a sum of ci times omega I, where the coefficients ci lie in the fixed field F. Compute the sum of yj times sigma j of x, expand sigma j across the sum, and here is the crucial step. Because each ci is fixed by every automorphism, sigma j leaves ci untouched. Regrouping the terms, the inner sum is exactly our system of equations, which is 0 for every I. So the entire expression vanishes, for every x in E. But that is a non-trivial linear relation among the distinct automorphisms sigma j. Dedekind's lemma absolutely forbids this. The contradiction means the degree cannot be smaller than n. So it is at least n. Both bounds are now secured. The degree of E over the fixed field is at most n, and it is at least n. Therefore it is exactly n. The degree of E over its fixed field equals the order of the automorphism group H. Artin's theorem stands proved, resting entirely on Dedekind's elegant lemma on the independence of characters.